Let's review quickly what we did in OCT, and then we'll move to nonlinear optics. Okay, so let's review this dispersion thing. Okay, so let's start here. So we're trying to understand the effect of unbalanced dispersion, meaning what if we have some dispersive material on one of the beams, one of the arms of the interferometer, and not on the other. And we had a discussion about what dispersion means and absorption and how they are related. So please, if you still have questions about this, maybe you can go to the 460 website also. That's how we start actually that class. Well, you're welcome to take it in the fall too. I had grad students taking it all the time. But really, think of the absorption and dispersion as the real and imaginary part of one complex response function, okay? So clearly, the dispersion is getting more significant closer to the resonance of the material. Now, in real life, in most of our experiments, lenses, beam splitters, things like that are made of transparent material for obvious reason, which means you're most likely you're way over here below the resonances from the UV, let's say if you have glass, right? But still there is this curvature in n versus omega that is not flat. So that turns out to make a difference. And what you're trying to quantify is exactly this effect. What if I have a refractive index that varies with frequency? So I have a dispersive material on one arm and not on the other one. And this happens intrinsically whenever you make an interferometer. I showed you in Michelson's interferometer, just by placing a thick beam splitter there, you force one beam to go through that glass twice more than the other beam. Okay, remember that? So one is going through once, and the other one is going 1, 2, 3 times. And we found out how to compensate for that. But first we wanted to understand the effects of the dispersion. Okay, so the way we do it is kind of as usual. We start in the frequency domain. So this is the cross-spectral density, U1 times U2 conjugate, and we assume they are identical on the two beams to begin with, on the two arms to begin with. The only difference is that one has a dispersive element, okay? The absorption, everything else is the same. So it means that these two together give you the optical spectrum, and this is the spectral phase that is different between the two. So now, in order to understand the signal, the OCT signal in the time domain, all I need to do is to do the Fourier transform of this. And that will mean, first of all, we expanded this phase in Taylor series. So this is a traditional way to doing things, because each kind of term or each power in frequency kind of belongs to a different phenomenon, or they get different names. It's pretty much the model from the aberrations I mentioned to you. Dispersion on time domain is the equivalent, is the analog of aberrations for an imaging system. Okay? So first we expanded phi in terms of Taylor series. So you have, this is a constant so we expanded around the average frequency omega naught. Yeah? So this is the 0th order term. This is the first order term. Okay? So you have the derivative. Let's go to the expansion right here. So I'm expanding around the mean frequency omega naught. So this is the 0th order term. The first order term is dk at d omega, because phi has k in it, right? Where is phi? This one. So because phi of omega is 2 times, because it goes back and forth, right? K of omega L, and this is basically n of omega times omega over c. Keep that in mind. The first order term will be dk at d omega at the mean frequency, omega minus omega naught. This is the first order. The second order dk d omega squared, omega omega naught. This is a parabolic term. So we're trying to understand the effect of each of these terms, right? And clearly this actually is not very exciting. Doesn't do anything, doesn't affect my interference at all. It's just a constant in phase. This is interesting because dk at the omega is something to do with the group velocity. Okay? So this is the group velocity because we have this broadband spectrum. We have a phase velocity, which is kind of the velocity of the carrier. And we have a group velocity, which tells you how the whole pack moves like, with what velocity that whole group moves, right? And in the case of dispersion, that group velocity varies with frequency. And that is exactly the second term right here. And we call that group velocity. Yeah, so group velocity is the velocity of the envelope. The carrier will be the one underneath. And when you have group velocity dispersion, which is this one, you see, it's d over 1 inverse group velocity at d omega. So it's kind of having an angular acceleration, right? That group velocity depends on the frequency. So imagine you have a pack of colors, a pulse, and now each color has a slightly different velocity. What's going to happen with that pack? I gave you the analogy with the soldiers marching. If they're marching in phase, they stay together as a group, right? Once their coherence kind of goes away, once the front goes to a different velocity than the back, they start to spread. So that's the effect of the group velocity dispersion. This is a very important kind of term in this expansion. This is what controls the amount of information we can pack in fiber optics, fiber optic communication, because this exact same phenomenon is spreading the pulses along fiber optics. Okay? So going back to OCT, let's see the effect of each of these terms. So this is the zero order term. So I'm here, spectrum times the spectral phase term. Zero order term, first order term, second order term. I'm going to take the Fourier transform of that to get to the cross correlation, because that's what I measure in OCT. It's just the Fourier transform of this whole thing. Okay, so I think I took them term by term. So yeah, so the first term, the zero order term is just here. So this really doesn't matter. So the first order term gives me 2L over Vg. So this is the group velocity, the Fourier transform of this whole thing. If we change the variable into omega minus omega naught, and I put the tau over there, I notice that I have omega minus omega naught, and my tau becomes tau minus 2L over Vg. So take a minute and do this by yourselves to convince yourselves, right? So basically, if I factor out omega from here and from here, I will get the tau minus something. So what it means is that this looks exactly like a Fourier transform. Now my variable is omega naught, minus omega naught, so I'm looking around the mean frequency basically. Okay? And what I get is going to be a gamma of tau, except it's going to be exactly what I had before. So this is a Fourier transform of the spectrum shifted at omega naught. It's going to give me exactly the autocorrelation function I started with. Except now the variable is tau minus 2L over Vg, is not just tau. And the meaning of this is very simple. What it means is that once I put a piece of glass in front of one of the beams, my interference shifts. How much? Exactly 2 times the thickness of the glass divided by group velocity. That's all it means. Altogether, what does this mean for my OCT experiment? It's not that bad. This doesn't affect my resolution, doesn't mess up my imaging much. All I need to do is to readjust my interferometer a little bit. So I don't know, displace the mirror to compensate for this shift. That's it. Cool?
What if you introduce something that has like a weird refractive index on the sample arm?
Like, what do you mean by weird?
Like some gel, some...
Okay, so why is that weird? Like, what do you mean weird? Dispersive?
Yeah.
So n versus lambda? Yeah, okay, so this is what we're talking about. The last term that I wanted to talk about is where there is a group velocity dispersion. So it's this term. Is that what you mean by?
So then what would you have to do to the other arm to compensate for that?
Okay, so we're talking about that next. Okay? So I wanted to tell you first, the zeroth order term plays no role. It's just a constant, right? But even the group velocity terms, what it says is that it's shifting the whole pack. Okay? No big deal. The interferogram stays the same width, which basically means the same axial resolution will be there. It's just translated, so you compensate with the mirror. It's exactly what we do in defocusing in a microscope. It's the lightest kind of aberration. It's not that bad. It's blurred, but it's fixable. I just adjust the focus, boop, no problem. The worst part of aberration is like spherical aberration in a microscope. Third order, which is exactly what we're doing now. So in that case, you cannot just fix it by playing with the focus. You have to do other things. So that's exactly the case with the second order term. So in that case, I'm going to have my original spectrum. Now, this is the second order quadratic phase term, Fourier transform of that. And notice it's a Fourier transform of a product. It's basically, the Fourier transform of that gives me the autocorrelation function that I started with, again, except it's now convolved with the Fourier transform of this, which is nothing more but also Gaussian, because I don't have a 2 here, this becomes a 4, remember that? And at the bottom I have the width of the Gaussian has the group velocity dispersion beta 2. That's the typical notation for it. And L, meaning that my gamma, my coherence function or the cross correlation function, gets fatter. How fat? Well, it depends on the width of the Gaussian. That has in it the material properties beta naught and L. The more material I add, the worse it gets. My interference gets fatter and fatter, and ultimately that is my resolution in Z. And of course, the material property, the more group velocity dispersion you have, the worse it is for your interference. Okay? That's it. So this is the equivalent of the higher order aberrations in an imaging system. There is no simple way to fix this. What you need to do, how would you fix this experimentally? How do you fix aberrations or dispersion? How would you do it?
Pay more money. You pay more money and get.
Okay, I kept telling you that you pay money for the objective. Okay, how did they do those objectives?
Simulation.
Okay, and at the end they give you a physical thing. So for these computer people in the room, simulation is not the end of the story. It's a means to get to an actual thing. So after you simulated the hell out of it, how do you fix it?
You compensate.
Exactly. How? You compensate, and I think that's how I leave dispersion compensation is a real thing that you have to do in OCT. But it's also very similar with the spatial. I like the spatial analogy because that's what you do with an imaging system. You compensate for those aberrations. How? My coherence function or my image becomes a convolution, right? Remember, in the spatial domain, even convolving with the Fresnel propagation ends up in a convolution, right? How would you undo that? Deconvolution. Numerically? So you're a computer fan too. Yes, numerical methods can help, but they're also limited. It's much better if we can actually compensate in a way from the bottom. So fix the aberrations before it kind of hits the detector. So what does that mean? It means we should operate right here in this domain. In a microscope, we should operate in the pupil plane of the objective, in the Fourier plane. So I have my plane wave incident, K incident, this is my sample, I get my light coming out, this is my objective, right? This is my Fourier plane right here. The aberration, all aberrations of this system are captured by a function that is exactly analogous to what we wrote for the dispersion. It's a spectral phase, which, when you let it go in the spatial domain, it becomes a convolution in the same way, right? So instead of having my beautiful U of k, which is the perfectly unaberrated frequency coverage of the image, it's going to be multiplied by e to the I phi of k. This is the aberration. Yeah? So clearly, when I take the Fourier transform, in other words, I put the second lens in my microscope and I make the image back at the CCD, this is going to be exactly U of R, so I take the Fourier transform of this whole thing. It's going to be U of R, my perfect image, except it's convolved now with the Fourier transform of whatever that is, e to the I phi of k. Yes? The exact same math, you see it? So, what I'm trying to tell you that it's always best to operate in the frequency domain because that's where it happens. So how would you do this for imaging? You need a device that is able to control the phase of this at that particular plane. So you need some kind of a device that is able to control the phase in a two-dimensional space. So such devices exist, okay? They could be a liquid crystal modulator, or spatial light modulator as they're called. It could be a deformable mirror. So the trick is to be able to first measure, kind of guess what this deformation is, and then put it up here and just do the opposite. So the SLM, let's say, will do e to the minus I phi k. And when you multiply it with your original one into the I phi k, it cancels out. That's the ideal picture. It never works that easily, but it helps a lot. So this is called adaptive optics. It was developed first for astronomy for clear reasons that looking at the sky through the atmosphere, this e to the I phi k is actually due to the turbulence in the atmosphere, right? So there is such a long path, even though air has such a low refractive index, when you multiply by kilometers of it, it starts to matter, right? So instead of having your diffraction limited image of the sky, you get blurs of them. Because of this convolution, that's just blurring, right? So people started to use aberration compensation or adaptive optics. Clearly, the name is very suggestive, right? This adapts to your environment. So in principle, under various atmospheric conditions, you can have a different filter action, right? So that means your device adapts and makes your points sharp again and so on. There's a lot more to talk about aberration correction and adaptive optics. And the main problem is that this is not known a priori. So how do you find it? Because it's very hard to measure the transmission function of the atmosphere, right? It's kind of not very practical to do. But people are smart, so what they found is look on the sky and find a spot that's very tiny below my diffraction limit. Basically, I know that the image of that thing should be the impulse response of my imaging system, right? Because it acts as a delta function. So I picked that. They call it, what do they call it? Not a marker, a star. Marker star? You have adaptive optics in your lab, right? Guide star? Maybe guide star. Okay, so I know this thing should be my PSF, should be absolute minimum in my image. So then you move this and do an iteration, a feedback loop, until you minimize the size of that spot. So once you did that, chances are you kind of hit on the correct frequency function of your aberration. And your image should actually, the entire image should now pop in greatest detail once you minimize that guide star. Okay, so more recently, actually, this was applied to microscopy. So it started with astronomy, and it ended up with it didn't end up, but it's very powerful now in microscopy. Actually, I saw these talks at the workshop very recently. There are a lot of the talks, light sheet, confocal, two-photon microscopy is actually adding adaptive optics on top. And the images look so much better. So if you want to learn more, actually, we have experts in the room, and also Kelly's colleagues in Professor Steve Bopart's room, lab. They actually published on this. And they also, Professor Bopart's group also works on the numerical correction. So you can combine the two actually to optimize the results. So you can also do a numerical deconvolution. I didn't want to dismiss that, but you can recognize that it's always best to remove the aberration before you detect it. Actually, that's always better. Even same thing with the noise, right? It's always best to do an interferometer that's common path and is stable instead of measuring a noisy signal and then try to get it out of your system. Okay. So, to recap, the only term that starts to make a difference is the second order term. And whenever the power is bigger than 2, so when phi of omega is omega to power n, when n is greater than 2, you're in trouble. And dispersion compensation is a thing. Yeah, so I showed you the spatial case. How would you do it with the spectral dispersion correction now? How would you do kind of adaptive optics for dispersion compensation? So like in the imaging plane, we need to be in the frequency domain, because that's where it all happens. Yeah? So how do we do that in the time domain?
In lasers, you can use the grading. And then,
yeah, grading is actually the way to do it. So basically, you take, let's say it's a plane wave, let's not forget about the spatial thing. So this has a spectrum that is broadband, let's say this is a pulse. Okay, so you hit the grading, there will be a zero order that's not very exciting, and then there will be the first order that will spread the colors. Which one is bent more, blue or red? Red. Remember, the angle is proportional to the wavelength. Yeah? So probably, and you get the -1 order and so on, and maybe higher orders. Usually what you do is you put a lens here, so you spread them like this. The zero order, I want you to remember, zero order stays white, which is kind of sometimes useful. All the colors go through the zero order as if there is no grading. That is the DC, that's the definition of a DC structure. Okay, but the first order spreads this according to angle versus lambda. So now, you are exactly in the situation that we were here. Right? So your Kx goes up from the origin to the, as the y-axis increases. Right? Here, my omega, well, it happens to go up as we go towards the origin, but who cares? Because the blue is here. Lambda is going up. So all I need to do is to use the same SLM. That will provide a phase of omega of my choosing. I can actually program that thing to delay pixel. The SLM doesn't know color, it only knows pixels. So I can program this pixel to give me this phase and the next pixel to give me this phase. And since I know which pixel is hit by which color, I really can modulate the spectral phase the way I like. And the idea is, again, to compensate. If this came with its own e to the I phi omega, you want this to make it minus phi omega, right? Okay? All right. And by the way, the interferometry again is going to, the interference signal will look like this. Depending on whether beta 2 is positive or negative, your spectral phase will go up or will go down. So like this. This will be positive chirp. Okay. Any questions about dispersion and how it affects OCT? Or low coherence interferometry in general. Keep in mind, Michelson understood this in 1870s. And he figured out a way how to fix his interferometer by placing an identical piece of glass on the other arm, the arm that had only one pass through the beam splitter. Any questions about dispersion? So by now I expect you to have an intuitive picture about why the interference kind of spreads out. It's because the group velocity starts to spread. Different colors go at different velocities. And you should be able to quantitatively actually write all these things down. And if you know the material properties, you know the beta 2, you know the thickness of that fiber or glass or whatever it is, you should be able to actually compute exactly how much it's spread, because that will factor into your axial resolution in your OCT system. It can really affect your resolution in the same way aberrations affects our resolution in the spatial domain. Yeah? So if there is anything unclear, let me know now. Yeah.
Do we have to know about phase velocity at all?
Do you have to know about phase velocity?
And for OCT, it's not really an aberration.
I mean, the phase velocity is what it is. So everything, the spreading of your coherence function happens. I mean, you should know the definition of it and what it means, right? But the resolution degradation is due to the group velocity dispersion. Okay? Phase velocity, keep it in mind with the GUI phase that we did in confocal. That's something maybe underappreciated, the fact that you get phase velocities higher than C as you simply focus the light down. As you go through the focus, you exceed the speed of light just because of the projection of the K vectors being shorter than K naught. Which is kind of, I think, interesting. Other questions about dispersion? No? All right. So we have an idea, at least in principle, how to fix it. Hold on. Okay, so what we said is, well, the way to do actual OCT, everything we discussed so far is kind of low coherence interferometry, which is, as I said, as old as Michelson. Low coherence interferometry was used actually right before OCT was published in the 80s. There were commercial devices that will tell you, will locate defects inside the fiber or a waveguide, right? And I mentioned how that worked. But imagine this is a piece of glass, a waveguide, and I want to figure out if there are cracks inside. You make your interferometer, you scan the mirror. Whenever the two paths match, can match with the path from a reflection inside. So if you have the cracking here, you'll get a spike in your interference. And this will report on a defect. And the position on the z-axis will tell you where it is inside. So Hewlett-Packard has a device like this in the 80s. OCT is taking this idea and applying it to tissues and actually get three-dimensional images, not just point measurements. Okay? So again, what we do is we replace the mirror with the specimen. The idea is to actually be able to recover the strength, how much backscattering I get from each position, and resolve that at each point in X and Y. You need to do some kind of raster scanning. Unless you're doing full field OCT, which is kind of a division of OCT, where you can actually use lenses and make actually images in parallel, like a regular microscope. That's why it's called full field, so you don't need to scan. But we're not going to talk too much about this full field, because actually, in terms of depth, resolution is inferior to the point scanning ones. It's very good for transparent, thin stuff, but when you go deep into the tissue, you have to do a confocal type geometry where you raster scan. Okay, so again, in terms of the math of it, basically, instead of your aberration, or in place of your aberration, basically your object is what creates that aberration. So one way to look at OCT is kind of in the other domain. So the traditional way is to look at the profile in Z, right? So I scan my mirror. Whenever the mirror path matches the depth from the object, I get spikes, right? So at the end of the day, I'm going to get some kind of a Z profile. But really, everything happens in the frequency domain. So you can think of it that basically what you're measuring is spectral modifications of the light on the sample due to the object. And it's not necessarily because the object is absorbing. It's not that it has very kind of fine lines or discrete lines of absorption in the object. The object could be perfectly transparent. But the spectrum can still change due to scattering. Because you have interference of different components, scattering depends on the wavelength. Altogether, it gives you a spectral modifier, pretty much like the dispersive function, except it has both amplitude and phase. So let me clarify that. So the dispersion function that we used before, up in there, it's e to the I phi, is completely, amplitude is constant. No absorption. Yeah? And also no, I should say, not only no absorption, no modulation. Because you can have modulation in the phase of a spectral function, not just through absorption, but let's say through a grating, right? So if I put a grating in front of a beam, I'll get modulation and amplitude, meaning the amount of red and blue power-wise changes. The phase may change also, but the power itself changes, you see? So the object is actually a complex function again, but it can have both magnitude and phase. So in other words, your object introduces its own dispersion, but it actually may operate on the amplitude as well. Just by the way each component, each omega is kind of scattered back from the object, right? And how it interferes with other scattering waves. That's basically a Fourier transform of this. That's what gives you the Z profile. It's the Fourier transform of this. Okay? So again, if we assume that the power and the two beams are identical, except for the object in one beam, then these two combined gives you the original spectrum. And when I take the Fourier transform of that, clearly the Fourier transform of my original spectrum gives me the autocorrelation function. And Fourier transform of H gives me whatever, H of tau, whatever that is. And altogether that gives you a convolution, because there was a product in the frequency domain. So again, really what it says is that if I have a profile Z, I don't know, that looks like this, various spikes from various surfaces in the tissue. I don't know, this could be your eye. This could be gamma of tau, which is Z, 2Z over C, something like that, right? So this is gamma. You can think of this entire profile as the convolution between gamma and H of tau. Gamma will be, do you remember what gamma is? It's just the narrow spike in the beginning. Could be this, the smallest feature you can detect. That's gamma. The fact that you have an object, you take this gamma and you convolve it with whatever the object function is. So in particular, if your object is made of one mirror we were talking last time, which is the way to make a delta function in depth, is to just put a mirror here. It will give you a reflection for that particular depth and nothing else. If you do that, you replace h with delta of tau, placed at tau naught, let's say. Instead of a delta function, what you get is actually this spread. Convolution returns the function. It simply gives you gamma shifted at tau minus tau naught. If instead of a mirror you have the entire object, which could be your eye with all these many surfaces in it, it could be like this. So these reflections may correspond to, like, let's say this is your cornea, that is this thick, so this will be one reflection, second reflection, and then this will be your lens, and so on and so on. This will be your retina. That's how these peaks are formed. But mathematically, it's nothing more but a convolution. It's that gamma for the autocorrelation function that is convolved with all these, the function of the object itself. And clearly, that's why we want our gamma to be so narrow. Because this gives me the resolution. If this gamma is fat, it's going to blur the entire thing. I'm not going to be able to distinguish anything. So that's why we want the spectrum to be broad. And even if you had the broad spectrum, you have to be careful about those aberrations that we talked earlier. Because this becomes convolved with the aberration function. That's what we showed earlier. That's why you need dispersion compensation. Any questions about that? So it's really a linear output, input, and this is PSF type of relationship. The PSF of your system in Z, or tau, is the autocorrelation function gamma. If you have dispersion, gamma becomes gamma 1, 2, the cross correlation function. We got gamma just because we assume they are identical except for the object. But if they're not identical, you have to reverse to the aberrated interferometer where you have actually gamma 1, 2. And on top of that, put the object. And we always know what we calculated is that gamma 1, 2 is actually gamma, the autocorrelation, so you can call it gamma 1, 1, convolved with e to the tau squared, that function, with the beta 2 at the bottom and L and the 4 and an I and the minus, I guess. The group velocity dispersion term. And I also told you last time that it's something very interesting and also might be overlooked, that the autocorrelation of each beam, of each field of the interferometer stays exactly the same. What degrades the resolution is actually because you cross-correlate them. If you were to use just one beam and autocorrelate that, it doesn't care if you put a kilometer of fiber or a meter or not, or nothing. Why? Because let's say my first field will have an amplitude and whatever, a phase of its own, and U2 will be the exact same thing except it's aberrated. It has e to the I phi of omega, the dispersion term, right? So if I cross-correlate them, I get gamma 1, 2 that is getting fatter. It's gamma naught or gamma 1, 1 convolved with that thing, with the GVD term. But if I do, if I correlate 1 and 1 and 2 and 2, what I get is that the spectrum 1 is actually U1 of omega squared. Spectrum 2 equals U2 of omega squared, which means no phi factors in. The Fourier transform of this will be gamma 1, 1. Fourier transform of this will be gamma 2, 2. No effect of phi at all. Meaning that it's only the unbalanced dispersion that matters for me. It doesn't matter that each beam has its own kilometer of fiber on. Nobody cares. As long as it's identical. Cool? Alex is still processing that. Another all-nighter? All right. So, in summary, maybe the greatest thing about OCT is that it's able to decouple the resolution, the axial resolution, from the transverse resolution compared to regular confocal microscope, where once you have an NA, or numerical aperture of the objective, that controls both ends, transverse and longitudinal resolution. OCT breaks that into two different pieces. You can use high NA and get a high X and Y resolution, so focus the beam down. But the actual resolution is controlled by the coherence function. In other words, you can actually have 0 NA, so illuminate with a plane wave if you want to go crazy, and you'll still have depth resolution controlled by the spectrum of the light, by the autocorrelation of the light. So that removes this constraint in confocal. Once you have very strong X and Y resolution, you automatically focus the beam in Z, so your depth of field is very narrow. You can only probe very small slice through the tissue. But if you are able now with OCT to open that up, you can actually control, you can go 1 millimeter in depth while maintaining kind of decent resolution in X and Y. All right. And if you Google OCT image in Google, you'll find a bunch of retina images. Let's talk about, which I showed last time. You missed it. Or you can go to Kelly's group meeting. So let's talk about, so we are now experts on resolution. And the special thing is about the axial resolution depending on the coherence function. How about contrast? What gives contrast in OCT? This is backscattering. So OCT is label free also, like the interference microscopy techniques that we talked earlier. So it's kind of as usual with the other microscopy techniques, with all the label free techniques. You want more scattering will mean more contrast. Up to a point. Too much scattering will mess up your entire image at the end. So what does that mean? Well, if your cell is in a kind of index matched liquid, your contrast will be low, right? So if you index match your tissue, it will be difficult to see it. So you don't want to index match perfectly. But now if you have the refractive index contrast too high, you will get multiple scattering. And multiple scattering essentially is destroying your interference signal. So basically these long paths, so these are depths inside the tissue. At longer and longer paths, if this is your tissue right here, you start to get multiple scattering, which basically will contribute an incoherent background here. Okay? Over short paths, you're more likely to get single scattering. So let's say scattered here, scattered here. So your OCT image will look great to the point of when the multiple scattering becomes dominant. And when is that happening? According to our scattering chapter, that happens at a depth of about the transform mean free path, which you remember is the mean free path divided by 1 minus g, where g is the average cosine of the scattering angle, which for tissue could be very high, very close to 1. And that's what allows actually the light to go deeper, because, so this is the average scattering the average length between two scattering events is roughly 100 microns for most tissues. It varies, but it's around there. But the fact that most of the light scatters forward, meaning this cosine is actually could be 0.9, could be actually 0.99 in some tissues. It means it multiplies. LT is at a factor of 10, could be 20 or sometimes 50 times the scattering mean free path. So this is actually, of the transfer mean free path is of the order of a millimeter in things like skin, maybe even below that. Of course, in the eye, scattering mean free path is larger than an inch, right? Because it's so transparent. So it's not the length of the tissue or the thickness of the tissue that matters. It's the scattering mean free path that actually puts a sharp brake on how deep you can image your density. And this is the motivation for developing photoacoustic microscopy or tomography to extend this, go beyond transfer mean free path. So use the depth penetration of ultrasound and the contrast of light kind of thing. So one of you probably is going to present on that. Who is that person? You? All right. Okay. So scattering is good for us. It gives us contrast. Too much scattering is not good. It's like too much of a good thing, right? And I think we talked about these definitions just as usual in microscopy. You need to take the noise into account. So contrast to noise ratio is not actually the contrast itself that matters. Yeah, so contrast is actually not great. The deeper you go, the lower it gets. But still, OCT made a huge impact, especially in ophthalmology. There are other applications that are being pursued at the moment. But ophthalmology remains the main application. Any questions before we switch to nonlinear optics? No? Okay, well, I thought I would talk for a couple of lectures about very introductory nonlinear optics stuff, because there will be some talks of nonlinear imaging techniques, and I thought we should at least have the basics down. There's a whole course of nonlinear optics taught by Professor Scott Carney, so I suggest you take that if you want to go deeper. But I thought I would present some of the principles just enough to understand, how a second harmonic generation microscope works, or two-photon fluorescence microscope. What's the basic principle, okay? So this is starting kind of very mechanistic point of view, which was, the picture is developed for linear optics, was developed by Lawrence, and this is how we start actually the ECE460. So Lawrence is the one with the Lorentzian. That's where the Lorentzian name comes from. And it comes from this equation, actually, except he started without the nonlinear term. So essentially, this little equation of motion assumes that you have a charge. At the microscopic scale, you have the electronic charge that is bound to the nucleus. And it's doing its thing, revolving around the nucleus. But what we are going to pay attention to is the fact that when I apply an optical field to this material, what's going to happen at the microscopic scale is that this charge is going to be displaced, trying to follow the E vector from my optical field. So basically, this equation of motion for, let's say, one single electron is very simple, the one of the mass on a spring. So this is the acceleration term, dx at dt2. This is the restoring force that has the resonant frequency omega naught, okay? This tells you that the electron is bound, or how strongly it's bound to the nucleus. So you see, we don't care that the electron is rotating, doing its own thing in there. We're only interested to the disturbance, to try to understand if I have an electric field this way, how is the electron going to respond to that? And then there is a term, a first order term, which is interesting, and it gave Lawrence a lot of trouble. He didn't quite understand what this meant. And I think maybe I mentioned to you at least once before. What is this? Friction. And what would that mean? It's kind of clear what it means for a mass on a spring. The resonance is the spring constant. Now, if I put this in a glass of water, the mass, it's kind of clear that will give me friction, right? What does it mean at the microscopic scale, at the atomic scale, for my charge?
Is it heating up the molecule?
Huh?
Is it heat for the molecule?
Heat is the eventual effect of it, the resulting. But what happens at the microscopic scale with that electron? This is a dissipation of energy, clearly, right? You said this friction, it is correct. How is the electron dissipating energy?
Radiation.
Nope.
Collision.
Collision. This was actually a hard term, so it's okay if it didn't hit you right away. This is the collision term. This gamma is actually kind of the average frequency for collisions. How many collisions per unit time does the electron undergo? So you see now, this little equation, forget the nonlinear part for now, is driven by this electric field. What's the electric force? It's the charge times the electric field of my, right? And we move the mass over here, but if you put the mass here, this is clearly an acceleration. This will be a velocity term, right? This is the restoring force. So this explains 95% of all optics, this little equation here. So this is how, this tells you the real part of the response, the refractive index. This tells you the absorption. This tells you the difference between, when this is dominant, what kind of material do you have?
A phase object.
Phase object.
Or transparent.
Transparent. Okay. Transparent. I know what you mean with the phase object. But so transparent, this is a dielectric. Meaning, what does it mean at the microscopic scale? Now you see what it means is that the electron is very well bound. There is no room to jiggle, to collide with the neighbors, right? That's a dielectric, perfect dielectric. What is this one? The opposite of that. Metal. Conductor. Perfect conductor. The electron is loose. It's free to move around. You hit it with a radiation, it's bouncing around, it's losing all its energy, your metal gets hot. Okay, of course, all materials are a combination of the two. Yeah? Okay, so the equation of motion, I don't think I solved this for the linear case because we did it in 460 right at the beginning. But we know what this is going to look like. Without much attenuation, you're going to get the sinusoid as a solution, right? Once you add attenuation, that sinusoid is going to die down. Nonlinear effects happen when you have here another term that is nonlinear in displacement. In particular, what did we neglect? When we wrote the electric force like this, what did we neglect right off the bat? Shouldn't there be another term? What's another force?
Magnetic.
The magnetic force. We left it all out. We left all that out. Nonlinear optics kicks in when that magnetic force is no longer negligible. And it turns out that one picture to explain that is that, as we all know, nonlinear optics happens at high power. What happens at high power is that your electric field is no longer going up and down on a linear trajectory. The trajectory may get curved. And I ask this every year, and it seems like nobody is riding bicycles anymore. When you were a kid, have you done this, like spinning the wheel upside down? You put the bicycle upside down and then you spin this like crazy to see what it does? No? Just me. Are you serious? Really? You've never done your bicycle upside down and do this, see if it works fine. Not that.
Just to put the chain back on.
Oh yeah, okay. And then didn't you do this to make sure it works? Okay. What happens if you really spin it really hard? If you spin anything really hard?
You say go the other way.
Well, the other way.
Aliens.
That's from the movies. Are you talking about movies when the carriages look like it's going? That's an aliasing, right? With the frame rate? Okay. No. But something more. Huh? Wheel will come off? Okay, if you go crazy, yeah, maybe. But before that point.
Maybe more stable?
More stable for a while. It looks like it's very, very straight. But did you ever reach the point where it looks like an 8 if you push even harder? It has to have an imperfection also, but okay. Another example. I'm sure you haven't used this if you haven't used the bicycle. My grandfather was a carpenter, so my joy whenever I was visiting him is to play with his tools. The most exciting one was a sharpener, this polishing thing, this stone for polishing tools. So that also, when you speed it, you turn it really high, it starts to vibrate, right? So if you put more power in it, it's as if the system cannot take any more power. It has to kind of go on to another degree of freedom to incorporate all that power. One way to look at it. Well, it's kind of similar thing to the charge. Instead of just going up and down on the direction of the electric field, let's say electric field on X, you start having components on the perpendicular direction. The moment you have a curvature, what kicks in? The Lorentz force, right? Lorentz force occurs when you have a curvature in the trajectory of the field. So, by the way, all this description is in a beautiful treatise by Blombergen, who actually got the Nobel Prize in physics for nonlinear optics in the 60s. His treatise was in the 60s. I don't know when he got the Nobel Prize. 68 maybe? I don't know. You check it. So it's very, very easy to understand if you read his original treatise on nonlinear optics. It's along these lines, okay? Whenever you can reduce it to mechanics, it's easy to understand. All right. So let's see. How do we deal with this now? So instead of just having an electric field here on your force, you have a second component that tells you it's when you do your right-hand rule and you do the cross product between V and B. Okay, don't look like you haven't seen this before, please. Do you know how to do the cross vector product? Do I need to review it? Okay, just for me, you would write this determinant down. So it's Vx, Vy, Vz, and then Bx, By, Bz. Okay? So we said I'm going to have an electric field on X, and I'm going to have a magnetic field on Y. So basically, this is 0, this is 0. So when you do the determinant, it's going to be this term that matters. So it's going to be Oh, I have two terms. Yeah. So first of all, I'm going to have. There we go. So I have this one here. So that's Vx by along x. Because I'm doing this, you're right, yeah. And it also makes sense because of that. And then I have another term, plus or minus. This will be plus, right? 1, 2, 3. This is minus? Oh, yeah. And then 0, 0 is going to be this one, like that. Vy times Bz, right? So this and times x. So that should match this. Okay, so they are the other way around. This matches this matches that. And they're both minus apparently, okay. Yeah? Is this okay? So this is the x component of the force, which has B.
Z is plus.
Yeah, but, okay, but I don't. Bz is 0, exactly. What the hell am I doing?
Vz minus Vz plus Vy.
So this should be minus Vzby. Oh yeah, because it's this one, this diagonal. So let's see if it now makes sense. So this is x, this is z. Okay, z dot is Vz, right? And then By, so that's good. And then this one is Vx, which is x naught, By. Woohoo! And I assume the signs are okay. See, it was useful to review the determinants. Okay, so this is where it's coming from. We're gonna the H vector. Okay, so I have the E incident and the H from the electromagnetic field coming in, and instead of just neglecting these, the H's or the B's, I'm going to keep both of them. And let's see the effect of that thing. The way we solve this differential equation in the most efficient way is to take a Fourier transform. Right? So we go into the omega domain. So again, the solution is for x. We're looking for the x displacement, y displacement, z displacement of the charge as I'm applying the electromagnetic field, and I'm keeping track also of the Lorentz force, which depends on the h, which is something that I neglected in linear optics. So Fourier transform of this equation, as usual, we have the minus omega squared. I see terrible grimaces in the room. Is it me or? Is this okay? Yeah? Okay. So minus omega squared minus I omega gamma plus omega naught squared is the resonant term. The linear response will be very easy. It will be E charge times E, the electric field, divided by mass. This will be immediately the solution. So my x of omega will be this thing divided by this thing. This is a Lorentzian, hence the name, due to Lorentz, who came up with it. But now we're going to keep track of this second term. So z naught Fourier transforms into omega z, right? And by of omega stays the same. So you have this product. And then z is going to have the same this response function here. This is kind of the linear response. And then the same thing, omega x, so x dot, the Fourier transform of that becomes omega x, by of omega. Yeah? So we're just solving those equations of motions, no big deal. So the solution becomes right away x of omega dividing the right hand side to the left hand side. So I call d of omega this part and b of omega this part. So basically b is the nonlinear part, that's why I called it little b to remind you of the magnetic field. When this is 0, you recover the linear response. Okay? So what we're after, we're trying to build the refractive index, or the chi response, the real and imaginary power response of the material at each frequency omega for the nonlinear case. I mean, linear and nonlinear, for the general case. Okay? That includes the magnetic response. That's what we're trying to do. So this is how you do it. Go in the frequency domain, you take the ratio, this is the solution. Now, let's take a look at what B means. I want to get an order of magnitude estimate for when, or what's the power level, or what's the condition for which nonlinear effects are important. So, when nonlinear effects are important is when Z, this component that in the linear response is 0, right? In the linear optics, X follows the electric field X. There is no Z. Your wheel stays linear, doesn't do this. Yeah? So, when these two, I want to know when these two become compatible or comparable in size. So if you take Z of omega divided by X of omega, you get something like charge times electric field divided by M, E, omega. E, this is the charge electric field lambda over MC squared with 2 pi. So what do you think that means? We got the MC squared in there. What is the numerator? E times EX is a force. It's the electric force that's doing a mechanical work over a distance equal to the wavelength. So this is that mechanical work. So when the mechanical work produced by the electron over the wavelength of light approaches MC squared, that's when you have significant nonlinear effects. And you can get actually estimates, you put numbers on the electric field amplitude if you want. If you estimate this, you get something, you pick a wavelength, I think I picked a micron or something. These are order of magnitude estimates, okay? So you get 10 to the 12, something like this. In the radians, you get something like 10 to the 20, 10 to the 21, which is, I mean, of course it varies a lot from material to material, but it's where it should be. So clearly, for the nonlinear effects to matter, you need a lot of power. Okay? How much power? Of this order. But I like this picture that gives you a nice picture for why the nonlinear effects matter. It's because it's when this mechanical force produced by the electron over one wavelength. So you're jittering that electron so much that the energy produced over the wavelength is of the order of MC squared. Okay? All right, but again, the key is in the magnetic field that is no longer 0, that takes care of curvatures in the trajectory. Okay. So there is something very interesting in nonlinear optics that we have to take care of first. we have to be careful about using complex analytic signals. So I think we discussed this in holography and I think several times, that all the fields in the lab that we measure, that we deal with, are real. We made up a complex representation for the real signal through a Hilbert transform, if you remember. We cut off the negative frequencies, right? Fourier transform back to time, you get something complex. That amounts to a Hilbert transform. We made it up so we ease our calculation. Instead of carrying sines and cosines all the time, we just use complex phase terms. The problem with this is now that, for example, if you compare where is this UR? Oh, this is UR squared. So the problem with nonlinear optics is that we're going to look at higher powers of the fields. So the response of the material will depend on the higher power of the field. Will depend on the field, which means that you're going to have U squared, U third, and so on. And that actually is a little bit tricky. If you just plug in the complex analytic signal, you get the wrong thing. So for example, my original real signal is A cosine of omega t, let's say. If I want to take the magnitude, or if I want to take the square of that, I can write it like this. It becomes amplitude square 1 plus 2 cosine of omega t. Okay? But if I write the complex analytic signal associated with this, is going to be e to the I omega t, A e to the I omega t. If I take the square of that, you get the wrong thing. Even if you take the real part of it, you get the wrong thing. You get A squared cosine of 2 omega t. You're missing the DC part. So we're going to use from now on the linear representation. And we'll see in a moment, for example, in the second order response of materials, like everybody knows about second harmonic generation, but what was surprising is that it's another term in there that is exactly related to the DC. It's called optical rectification. It's the effect of the same nonlinearity, the one that gives you double frequency. There is another term that gives you zero frequency. So if you imagine you hit a crystal, it gives you double the frequency. You get from infrared to green, for example. But if you measure carefully, you'll find also DCs, like a battery voltage in there. And people actually measure that. That was surprising. So if you don't use the real representation of the field, you'll miss that. Okay, so let's look at the second order nonlinearity. So what if I have here that term, the nonlinear response, captured by a square term in X? This is what we mean by a quadratic nonlinear. Okay? So in other words, your swing or your spring or your electron on a spring is not actually harmonically going. It actually has a nonlinearity in there. So what it means is that for example, the more I stretch the spring, the stronger it gets. Okay? That's a form of nonlinearity. A linear system will mean if I have a spring, it doesn't matter how much I stretch it, the constant stays the same. Right? The force gets bigger, it becomes k times x all the time. Okay? But k stays constant. Nonlinear means that k is proportional to x, and the force becomes kx squared. This is where this is coming from. Okay? By the way, there is a lot of this nonlinear stiffening in cells, actually. If you stress a cell more and more. We actually measured these in red blood cells, that if you blow them up, if you stretch their membrane more and more, the elastic constant changes. It's like a stretch spring. Okay, so that's kind of how I want you to picture that. So how do we solve this? Well, unless you linearize the problem, unless you consider that the displacement due to the nonlinear interaction is much smaller than the first, than the linear response. So we assume that actually the nonlinearity is not that big. This is very difficult to solve. So as you know, nonlinear differential equations you can only do numerically. It's not easy. So what we always do, or at least we try to get the physical insight first, by doing a first order perturbation theory, which is exactly saying that my solution, X, will be dominantly due by X1 and a little bit by X2. So X2 is very small compared to X1. This is exactly the same mathematical approach we did with the Born approximation, if you remember, right? So U1, the scattered part, was there, but it was a small perturbation on top of the incident plane wave. Remember that? Okay. So basically, if you insert x1 plus x2 in the original equation, you get the linear one, so this is the linear equation, plus everything with x2 in it. Okay? So, you see it? So this is the x1 part. We're going to separate the linear response, which is the x1, from x2. And because I have x squared here, I'm getting 3 of these. So this will be, up to here is kind of a linear equation in x2. And this is the ugly part. So I have x1 squared, x1, x2, and x2 squared. So I'm going to neglect the source terms that have x2 in them. I'm going to keep only x1 squared. So the spirit of this is exactly the one in the Born approximation. What it says is that the nonlinear response is driven, the source term has only the linear part in it. It's exactly what we did in the Born approximation. When we put on the right hand side, we replaced the total displacement, which was supposed to be these two, with only the incident light. Remember that? Hello? Actually, it's time. Do you remember that? We're not living until you nod your heads that you remember the Born approximation, that we did the exact same thing. Do I need to write it down? So we had this. Squared, Laplacian of u of Rn omega plus beta naught square, and here we had n naught square u of Rn omega. And we moved the inhomogeneous part to the right, and we had minus chi of r. We had beta naught square here. And here we are supposed to have u1 plus u naught. Right? And we said, inside the scattering medium, pretty much my plane wave stays undepleted, approximately, right? So in the source term, we deleted U1. It's exactly same approach of first order perturbation theory that we're going to use here, okay? So we have the linear equation for x1, the nonlinear equation for x2. The full solution will be x1 plus x2, but we don't care about the linear response. We know how that looks like. We're going to focus on x2. And basically, we're going to use the solution x1 from here, which is easy to do, and plug it back into here. And we're going to see the kind of terms that we get out. Right, so clearly, because you have x1 squared here, you are going to get second harmonic generation, right? You're going to get double frequencies somewhere. That's the plan, okay?